All right, welcome back. Today we are going to move along into three-body decay. We haven't said everything there is to say about two-body decay, right? There's still a lot on the table there where we have to talk about opening angles and the momentum of a particle. We calculated it in center mass frame, but we are curious about the laboratory frame for the energies of particles. So we're going to get back to that, I think, but I want to just keep moving into three-body decay because three-body decay is a very rich subject. It feels kind of like particle physics, even if if you do other forms of physics like I do. Studying three-body decay kind of gets you into that groove of really feeling like you're analyzing stuff coming out of an accelerator. So it's really, really interesting. Our ultimate goal here for the three-body section, I think a fair goal is to understand what is called the Dalitz plot. The Dalitz plot is a way of analyzing momentums of particles in a coming out of an accelerator, or particularly in a three-body decay process. Looking at some of the experimental data, they get put into a Dalitz plot, and from there they evaluate and understand all kinds of things. In particular, from a Dalitz plot, we're going to study the most elementary form of that because that's accessible to us. The parts that we're going to leave on the table for now is the spins of the particles involved in the decay and any resonances, right? Any sort of resonance particles that might exist in the middle of this decay process. These are interesting and advanced topics. I hope we can, I think we can touch on resonance. Resonance will be accessible to us. Getting involved in all of the angular momentum properties of this stuff is a little bit outside of just your pure relativistic mechanics, which is what this lesson series promises to cover. Anyway, so let's get started with three-body decay, and let's begin. So the process of three-body decay is the diagram. It's going to have a very similar structure as the two-body decay. We're talking about a parent particle that will disassemble into three particles. The timing, mechanics, dynamics of that disassembly are not part of our work. That's part of, again, quantum chromodynamics, quantum electrodynamics, and all those forces you know about except gravity are involved in when and why and how this particle might decay into three different child particles. But this picture kind of is implied to be in the center of mass reference frame of the parent particle. We sort of see this isotropic decay process where these three particles can kind of go in any direction, and that greatly complicates three-body decay over two-body decay, where in the center mass frame of the parent particle, the child particles always had to have three momentum that were counter-aligned. But that's no longer really the case here. It all will depend on the mass of these particles. These particles could have well-defined rest masses, depending on the decay process, but the energies that are distributed among them and the directions they go are now much more accessible. And the language we use is the phase space of the decay products is now suddenly much bigger. The phase space meaning the energy and momentum of all of these particles can be larger. And the Dalitz plot tries to get a handle on the size of the phase space for these three particles, which will become clear as we move along. So another thing is in a unique difference between 3D and three-particle decay and three-body decay and two-body decay is that there's more reference frames to choose from. In two-body decay, it was the center mass frame and the lab frame or our two big frames. In principle, you can go into any frame, right? You can go into the frame of particle 2 or particle 1 in a two-body decay. But in three-body decay, you actually have a lot of frames. You could go into the frame where where the subsystem 1 and 2 has a center of mass, right? There's a center of mass between these two particles. You could be in that frame where the center of mass, where the four momentum of the center of mass of these two particles is zero. Same with this subsystem and this subsystem. And each of those subsystems has its own invariant mass, as we're going to see in a moment. Well, that moment has arrived. Let's just write it down right here. The overall conservation of momentum for a three-particle decay is exactly the same as it would expect. the children on the right, the total momentum there must equal the total form momentum on the left. And remember, we're dealing with form momentum, so this includes the conservation of energy. It's all bound together. The energy is the time-like part of the 4 vector. So with this, we can form more invariants. Right now, the invariance that we're used to is the mass of the third particle, right, would be P3 squared. That's the mass of particle 3 squared. So that's an invariant. Likewise, you get an invariant for mass of 2, mass of 1, and mass of the parent. But there are these other invariants, right? There's the S1 invariant, right? The S1 invariant is the mass of particle, is the invariant mass of the sum of particle 2 and 3. That would be sort of what we talked about a moment ago. That subsystem has an invariant mass. It's also equal to the square of the parent particle minus the child particle that's not part of this center of mass. And likewise, you can do it for all 3 combinations. You get S2 and S3 for the 1,2 subsystem and the 1,3 subsystem. And all of these 3 have an invariant mass, and it's a completely legit invariant mass. However, there is no single particle that embodies that mass. This is you have sort of a hypothetical particle that has the momentum of the sum of the particle 1 and particle 3 masses. And this is a well-defined invariant quantity that won't change regardless of your reference frame. So a lot of 3-body decay, well, I'm not even going to say a lot. All of our analysis of 3-body decay digs into all of these invariant masses, the regular invariant masses of the particles and the invariant masses of the subsystems. And it's all part of making the algebra as useful and as understandable and as workable as possible. Okay, so we're going to be doing our math, and sometimes these invariant masses, in the decay process, we just call them, invariants. Usually when you're talking about collision processes, they get called Mandelstam variables. And then there's questions called momentum transfer and some other terms that we'll learn when we talk about collisions. But these are sort of the Mandelstam variables associated with decay processes. And we're now going to work with these variables. All right, so let's exercise some of this by just doing some really basic things, right? We're going to do a basic demonstration of a property of these Mandelstam variables. But just consider S1, the first interesting one, the subsystem of particle 2 and 3, which we decided was sort of the mass of the 2-3 subsystem. And let's just blow it up, right? This is the definition of S1. So we can blow it up. Remembering these are 4 vectors, so we get P2 squared, P3 squared. And as it's a 4 vector, we get these dot products. This dot product cross term is completely legit. And when we talk about, I'll just warm you up now, when we talk about going to different reference frames, in the elementary study of this stuff, that almost always means we're trying to find a reference frame where we can make these dot products really simple, right? And that's the trick. When we go to different reference frames, that's the goal. The goal is you're dealing with things. This is always true, no matter what reference frame you're in. But when we want to figure out what these dot products are, we choose a reference frame to make it easy. And you'll see a couple examples of that in this lesson. So I can write this expression down for all 3 of these guys, right? P2 and P3, remember, that's the invariant mass. You've got to immediately recognize that when you're dealing with momentum, and you see a 4 momentum squared, that is basically an invariant, and it's the invariant rest mass. We call that the rest mass. So P2 just becomes M2, P3 becomes M3, and there's nothing we can do to simplify this. And then S2, likewise, you'll have M1, M3, and S3, you'll have M2, M1, and then you have these cross terms. So now let's say, so that's the first thing to understand about these invariants, but now let's add them all together. Let's add up S1 plus S2 plus S3. And adding them up's not hard. You get, from S1, you get an M2 squared, but you also get an M2 squared from S3. So you end up with 2 M2 squareds. Same with M3. There's 2 of them here. You end up with 2 of them, and same with M1. So that's where this factor of 2 comes from when you add up these invariant masses together. When we add up these invariants together, you get the 3 invariant masses times a factor of 2, And then you get all of these cross terms thrown in there as well, right? So now, again, there's always some clever piece to this relativistic mechanics algebra, but we take these two masses and we break them up into one sum of masses and then another sum of masses to which we add the cross terms, right? So we've got these two parts now. We've got the cross terms added to the sum of the of the rest masses, and then we have the sum of the rest masses again. But now we are going to learn that this expression here, right, that actually equals the mass of the parent particle. And therefore, the real result is the three masses plus the mass of the parent particle, right? So the total sum of all the rest masses is equal to the sum of our three invariants. But we have yet to show that. So let's show that. And the way we show that is we go right to here and we just use the obvious thing. We're going to write down the total momentum conservation expression for the entire process. The form momentum of the parent particle equals the sum of the form momentums of the daughter particles. And what I'm going to do is notice if I cast this in the center of mass frame of the parent particle, I would substitute this vector p for m and 0. And that's your telltale sign that you're going into a specific reference frame, is when you take expressions for four vectors and you break them down into the literal four vectors where you're writing down components. Because you have to make decisions about those components. And in this case, we made the decision that the three momentum would be 0, which is the definition of being in the center of mass frame of the parent particle. And when we do that, notice I made no distinction over here, right? This is just E1 row 1, E2 row 2, E3 row 3. That's P1 plus P2 plus P3. And this doesn't define any particular frame. These are arbitrary. But because I have that 0 here, this equal sign gets a little circle on top, meaning this expression is only true in the center of mass frame of P, or a particular frame, right? And the particular frame is the center of mass of the parent particle. But regardless, the next step I write down is not dependent on what reference frame you're in, right? I'm just calculating P squared, which is I'm squaring this expression. So I square this sum of three terms, and I get this long expression right here. That's what that square looks like. It's these three P squareds plus these three dot products, all with a factor of 2 in the dot products. And you can just square it and you'll get that. But what's interesting is, as soon as you get that, as soon as you see P1 squared, what did I tell you to think of? Well, you got to think of, that's the mass of particle 1 squared. And P2, that's the mass of particle 2 squared. And P3, that's the mass of particle 3 squared. And then these guys here, I just bring them down, and I get, and P squared is this the mass squared, right? So then I get this expression, right? That the mass squared of the parent particle is the sum of the masses of the child particles plus 2 times these dot products, right? Which makes a little bit of sense, right? You can imagine that, say all these dot products were for some reason 0, the mass of the parent particle would exactly equal the mass of the child particles. And those child particles would just appear without any velocity, I guess, right? They would be sort of motionless. But anyway, the point is this is the expression you get, which of course is exactly the expression that was remaining over here, right? And that just tells us that the sum of our three subsystem invariants is equal to the sum of all the mass invariants, right? So a nice little expression there, and you get to exercise some of these algebraic manipulations of four vectors. All right, so now something to notice here is the left side and the right side are both invariant quantities, which means that this is true in every single reference frame. It doesn't matter what expression you get, which of course is exactly the expression that was remaining over here, right? And that just tells us that the sum of our three subsystem invariants is equal to the sum of all the mass invariants, right? So a nice little expression there, and you get to exercise some of these algebraic manipulations of 4 vectors. All right, so now something to notice here is the left side and the right side are both invariant quantities, which means that this is true in every single reference frame. It doesn't matter what reference frame you're in. So notice over here, when I was doing this calculation, I skipped from this line right here. I skipped all this stuff and I went right to the end. And the reason is because the first time I did this, I didn't notice, the most naive thing. I didn't notice. I did what I told you not to do. As soon as you see P1 squared, P2 squared, and P3 squared, immediately replace it with the masses. I didn't do that. What I did is I went into this reference frame here, and I thought there would be some advantage going to the center mass frame. So I calculated m squared here, and then I squared this thing, and I ended up with E1 plus E2 squared minus these magnitudes, these minus the sum of these magnitudes squared. That's just what this squared would be, right? If I square this, you get, E1 plus E2 plus E3 squared minus the magnitude of rho 1 plus rho 2 plus rho 3 squared, right? That's how you square a 4 vector, right? So that's what I literally did. And then I had to blow these guys up, which took forever. And then I recombined these guys. But if you recombine these guys, you realize, oh, that's just the mass of particle 1. That's just the mass of particle 2. So I basically went from here to here, and I then went back to here. So I jumped into a reference frame when I didn't need to, is my point. And ultimately, when you combine all these together, that is all derived from this and the cross products of this. And when you recombine everything, you end up here. But you never needed to go to this special frame. But I did, and I just had a lot of fun, but I was pretty inefficient. But anyway, the point is, one point that I want you to take away from is that everything here in the end is totally invariant, right? And it doesn't matter what frame you do these calculations in. You'll always get, these masses clearly don't depend on the frame, and it turns out these S's don't either. Everything is invariant. So what would a variant thing look like, right? For example, and I'm going to show you now, we're going to do a calculation where we calculate something that is not an invariant. But these things that we're going to calculate, we're going to go to a specific reference frame, we're going to calculate something that is not an invariant, and ultimately we're going to use all that to help us figure out and derive limitations on what kind of momentum the children particle can have. So I'm choosing these invariants, these non-invariant quantities very carefully. All right, so first let me say I'm using this word variant. That's not standard. I've never heard a physicist out there say, oh, it's a variant quantity. They usually say it's not invariant. Invariance is so important that they're happy to live with the double negative for whatever reason. But what would a variant quantity be? Well, if I said that P1 was equal to E1 over rho 1, and then I find a way to calculate rho 1, right? Maybe the magnitude of rho 1 squared. Maybe I find a way to calculate that. That is a variant quantity because you're not calculating a 4 vector or a tensor or a scalar. You're calculating a part of a 4 vector in this case, or one component of a tensor, one component of a 4 vector. Those are always non-invariant quantities. And so right now, I want to calculate exactly this one right here. I want to calculate the magnitude of the 3 momentum of the first child particle. I want to do that calculation. And then I also want to eventually calculate this energy of this first child particle. And I want to calculate the energy of the third child particle. And with those 3 energies, the next lesson, I'll be able to use that to construct constraints on what these momentum can be, the constraints on the phase space of this decay, as we'll call it. And but I need those three quantities. And so we're going to build it up by first calculating these three quantities in this lesson and then putting them together in the next lesson. All right, so let's begin by writing down S1, which is the 2,3 subsystem, and it's the square of the two form momentum of particle 2 and particle 3 in the decay. And so it is the mass of the 2,3 subsystem. So now, what is P2 plus P3? So let's write down P2 plus P3, and it's going to be E2 rho 2 plus E3 over rho 3. But I'm going to declare myself to be in the center of mass of the 2,3 frame. I'm arbitrarily saying that that's the frame I want to work in. And the definition of that frame is that the sum of these two have to have 0 3 momentum. So I put that in. And as soon as I put that in, I have to change my equal sign to an equal sign with a circle on it to remind everybody we're now dealing with something that is an equality that is only true in one particular frame of reference. And that happened the moment I put in this 0. Because this is totally general, and this is totally general. And this would be totally general if I wrote rho 2 plus rho 3 there. If that was there instead of the 0, then I wouldn't need this little circle, because it's true in any reference frame. However, because I'm asserting that I'm in a specific reference frame, I'm now going to have to include it. Okay, so now with that, let us remember that P minus P1 is another, this should be P2, P3, right? P minus P1 is another way of writing P2 plus P3. And so I'm going to now write that down here. This is P1, totally arbitrary. This is P2, this is the parent particle, P1, or P, and then P1 is the first child particle. These two are totally arbitrary. But in this reference frame, it's going to equal P2 plus P3, which we just calculated up here, sort of by just asserting it was in the CM frame. And because that 0's there, and we're in this 2,3 center of mass frame, this equation is true. And the reason this is important is it tells us that the momentum of the parent particle and the 3 momentum of the parent particle and the 3 momentum of the first child particle in this reference frame must be the same. And that's this statement right here. Right? And you can see the little circle there in the equal sign. And that's important because I can now lose the 1 and I can just talk about rho. So now I write down S1 in this reference frame. It's P minus P1 squared. Well, that's going to be, because rho has to equal rho 1, rho minus rho 1, that's going to be 0, right? And so now I can write E minus E1 squared over 0. And this is super easy to calculate, right? I don't have a magnitude of 3 momentum term, right? If this was not 0, I would have to square this and subtract the magnitude of this 3 momentum squared, which I don't have to do now. So now I just take this minus this. But what is E for the parent particle? Well, it's the mass of the parent particle minus the momentum of the 3 momentum, magnitude of the 3 momentum squared of the parent particle. And E1 is the mass of particle 1 minus the 3 momentum squared of particle 1. And notice that this row, these two rows are now the same because we are in the 2,3 reference frame and we just calculated them to be the same. I'm going with rho for the momentum, by the way, because if P is the 4 momentum, it's kind of difficult for me to write E and like little p, you know. I know my little p's and my big p's are going to get confused. So I've gone with rho down here for the, I'm still going to put the vector symbol on it. So, but the point is this rho, even though it looks like the rho of the parent particle, it's also the rho that we're after, the rho of the first child particle. Okay, so that's our next step, right? We just made this subtraction right here. We know that E is literally defined this way, and E1 is literally defined this way. So now I need to solve this. I have an invariant here, S1, in this particular reference frame, and everything, and M squared is an invariant, and M1 squared is an invariant. So I can solve for this non-invariant quantity in terms of all of these invariant quantities if I can just isolate rho. And if you look at this, you may remember in lesson 2, we were faced with the exact same algebraic problem. We had the difference between two radicals, and under each radical was another difference, but the second part of the difference was the same, right? And we want to solve for rho, right? We're interested in solving for this guy right here. And this shows up a lot in relativistic mechanics. This very problem of teasing out something that's buried in these radicals inside a square. We did it entirely in, I think it was lesson 2, but it was on our two-body decay. Might have been lesson 3. But we did it. We exercised the whole thing. And we ended up with this result, right? That rho, the magnitude of rho square in this particular reference frame is this function of all these invariants. In this case, it'll be the function of S1, M, M1, the mass of the first particle, the mass of the parent particle, and this S1, which is basically the mass of the 2,3 subsys system. Remember, this is the mass squared of the 2,3 subsystem. And now when we did it, when we went from here to here in the previous lesson, all the symbols were different, the circumstances were different, but the mathematical architecture was identical, and you can go back and walk through it if you want. I try never to say, oh, trust me, this is the case in the lessons that I put on for this kind of coursework, but we already did this, so I'm not going to do it again. But this comes up so often. It turns out that this expression right here, this part right here, is so common in particle physics that they actually just gave it a name, and they called it lambda. And when they define lambda, they actually define lambda this way. So it turns out that this, taking a squared plus b squared plus c squared and subtracting off twice these cross terms, that is the same as this, right? And when we did this before, we ended up here, and we had to prove that to ourselves. We had to convince ourselves these two actually were the same. And so now we have an expression for this non-invariant 3 momentum magnitude in terms of these invariant quantities. And that's what we're talking about for a moment. Because how is it? I mean, this is an invariant. If you got an invariant on the right, shouldn't you have an invariant on the left? Doesn't matter what reference frame you're in, S1, M, and M1 are never going to be different. So if this thing turned out to equal 9, it doesn't matter what reference frame you're in, right? I could be in a reference frame or not in a reference frame. I'm always going to get 9. So this invariant, that just seems weird. But the answer is that this value of 9 equals the mass, or equals the 3 momentum of the first child particle only in one reference frame. In all the other reference frame, yeah, this will still equal 9, but that 9 cannot be interpreted as the spatial part of a 4-vector's magnitude. The magnitude of the spatial part of a 4-vector will not be 9. It'll be some other number. And what this is, this invariant value, will be much harder to interpret in some other reference frame. But in the reference frame we're in, it actually is this invariant magnitude. Okay, that's a really important concept. That took me a while to understand. I was sort of stuck on that for a bit. I was like, there should be something non-invariant over here for this to be non-invariant. But no, it's just the way you interpret it. The interpretation only makes sense. Okay, so we have now solved one of our problems, right? We have calculated this value, this part of this 4-vector in one particular reference frame. Now let's go after E. Well, actually, I'm out of time. I want to keep these things down to a half hour each. So in our next lesson, we are going to calculate E1 and E3, and we're going to start talking about constraints on the phase space or the possible momentum of these child products. See you next time.